So I'm going to start with some slides and then show some code, and then I'll go back and forth. So my name's Johnathan. I'm a tech in Nick Records lab here at Bigelow. I'm calling in remote though from my house in Brunswick, Maine today. And Nick, in organizing the OceanHackWeek, was telling me a lot of people are asking, or we're asking for some machine learning content. And my project working with him is using deep learning in R. So I'd like to introduce deep learning and I guess maybe give some broader context just on AI in general. And I've also, just with interacting with other participants of the OceanHackWeek, it seems like there's a wide range of experience levels with machine learning. Some people that seem like they're way further down the road than me, and some people that just want to get their feet wet. So I'll try to keep it general, and if you don't understand everything, please ask questions. And I guess I'll jump right in. So to start, I really like this figure. I've been shown it in a few talks in the past few months. So AI is popping. Everyone's talking about it. We're definitely in like a boom cycle, and you see it in media and lots of papers and lots of different industries. But what exactly is it? Simple definition is it's just a way you can automate a task that a human could also do. And this concept is not new. While it's being talked about a lot lately, the first AI systems were being developed as early as the 1950s. And these were called rule-based, which were essentially just programming a list of rules and into an algorithm, and that algorithm could make a decision that a human could equally make as well. But then these systems started to reach their peak by maybe the 1980s, and they still couldn't solve really complex problems or fuzzy problems that don't necessarily have a yes or no answer. The answer is somewhere in between. So this was the birth of the field of machine learning. And so there's a bit of a paradigm shift from taking a set of rules and putting some data into an algorithm, and out came some answers. Researchers started to ask, could a computer learn these rules instead of us figuring out what they are and programming them? So they started to say, okay, well, if you take your data along with the answers you'd expect for it or the targets you're looking to achieve with that data, put it into these algorithms, and out comes a set of rules. And this set of rules is a representation of the data. We refer to it as a model. And with this model, you can then predict on data that the algorithm hasn't seen yet. I added in this supervised machine learning because this specific paradigm of data along with the answers is referred to as supervised, but there are other facets. And deep learning is an even further subfield of machine learning, where you're dealing with lots of data and you need multiple layers of increasingly meaningful representation to learn that set of rules or to model that data. And one other thing I'll say is, when I refer to training, that's the learning process. You're training your algorithm. And before I go any further on deep learning, there are a few types of machine learning, supervised being the most common, and that's most of what the AI that's being done now is using, and that's data with labels. Some examples of this could be classification, binary, so yes or no, 1 or 0 answer, or multi-class with infinitely many options. And you could also do regression, where you're predicting on a constant scalar value. You can also do unsupervised learning, which is where you're just putting the data in, no answers, and expect the algorithm to, find some representation of that data or some parts of it. And so examples of this that are commonly used are like principal component analysis, clustering, or dimensionality reduction. There's also reinforcement learning, This is where your model we would refer to as an agent, and it's in an environment where it's receiving information and it needs to make decisions. And so you set up a reward or punishment system so it knows what decisions are right, what decisions you don't want it to make, and it can successively get better. And examples of this would be like a self-driving car or even like an autonomous underwater vehicle. Self-supervised I threw on here, but I really don't know too much about it. But I thought it was worth mentioning that we have so much data now that sometimes there isn't enough time to go through and label every point. So you actually use an algorithm to label it first and then use that as an input into a supervised machine learning model. And some cool ocean related machine learning examples I have been reading about. So the first two are kind of similar, where you can have images that are coming through. So one is in a trawl net. So for a trawl survey in fisheries management, rather than bringing back all of the fish that you catch for that entire trawl, you have an open caught end on the back of the net. So everything that comes in goes right out the back, but you have cameras tracking all the fish coming in. And with these images, you can get counts on, the number of fish, but also the species and measurements on length. The other way this is used is for electronic monitoring, where you could have cameras installed on a commercial fishing boat instead of requiring them to take an observer to, measure fish and count fish. And so this picture here in the middle would be like a camera above a conveyor belt where they're processing their catch. And finally, these USVs, unmanned surface vehicles, definitely becoming more and more important as there are gaps in oceanographic data we need to fill. And this is an option where you could have an unmanned vehicle go out and collect that data for you rather than using a mooring or on a ship. So deep learning, this whole tutorial is on deep learning. That the principal algorithm used is called a neural network. They are super complicated. This idea could be, or this field, could be put into an entire semester course or even, a whole PhD thesis. But very simply, I always like to remind myself, all that's going on, you're putting numbers in and numbers come out. And it's called a neural network because it's loosely based on the learning patterns of a human brain, but don't let someone tell you that it's mimicking how a human brain learns. So some basics on the mechanics of it. We have multiple layers to represent this data rather than just one. And so we're taking an input, X, this would be the data point, and we want to get to this prediction Y, which is the answer. And we have multiple layers. In here, you see there are multiple nodes in each layer. And during training, the learning process, it'll flow the data through and then determine, did it classify that right, or how far off was it in that regression? And this gives us a loss score calculated by the loss function. And then this is passed to an optimizer, which is what updates the weights, which are the connections between all of these nodes in the networks. Don't have time to explain all of these different types, but I like this little figure to show that there are lots of different flavors of neural networks. And today I'll be showing an example that uses TensorFlow with Keras. So TensorFlow is an open source project from Google. It's hardware independent and it runs equally well on CPU or GPU, or multiple for that matter. And it's really built for scalable deployment for very large data sets. And the reason for this is it doesn't require all of your data to be in RAM at once. The optimizer, what's actually learning, doesn't need all of that data. It works equally well if you feed in batches of data. Keras is the higher level API that wraps up lots of lines of TensorFlow into functions where you can build layers, models. There's lots of options for optimizers, loss functions, etc. And Keras, because they've wrapped up so much of this TensorFlow code, allows for rapid development. So you can cycle from idea to experiment to result and then back to a new idea really quickly. And a little spoiler, I guess you'll see a little bit of that in our drone turtle project presentation tomorrow. And even further, they've adapted Keras for R. So originally I was going to show RStudio, but yesterday or the day before, I wasn't able to get my R markdowns to run. So I had to change them all to notebooks. But the point I wanted to make is that you don't need to know lots of programming languages or super technical programming languages for that matter. I know in the life sciences, often people, if they only know one language, may know R. Now they're capable of implementing deep learning models and running those experiments. So TensorFlow, tensor means multi-dimensional array. You can have, anywhere from 2 up to, I show 5 here, but my example will be on forecasting. So we have, a number of samples by the number of features in there, and then the number of time steps you're using to forecast. So I'm going to get to the first tutorial now, but I wanted to show this figure, which is a representation of what's going on. So we have this large data set of handwritten digits. It's called the MNIST data set, and often referred to as the Hello World data set for deep learning or machine learning, I guess, for that matter. It's used to test lots of algorithms. And essentially, we just have 60,000 examples of handwritten digits, 0 to 9, and the goal is to classify. And I like this figure because it shows how in each of the layers of the neural network, the data is just being transformed slightly all the way down to get to this final output of selecting, 0 to 9. So I'm gonna get out of PowerPoint now, and we'll fire up the Jupyter Hub. Also, any questions so far? I should look.
There's no questions so far.
That's sweet. So if you're on your Jupyter Hub, you're going to navigate to this deep learning directory and then open up this #1 number classification notebook. If you're not seeing this, you may need to do a git pull, but if you're using the NB git puller link, it should all be in there. So I'm going to start out. We're going to load these libraries. Again, this is R code, but in a Jupyter notebook. So some of the outputs aren't as nice if you were doing this in RStudio, but we'll work with it. We have to set the right environment. We're telling R which Python to look at. And this is one of the biggest challenges, I'd say, even more than understanding, how to build the models and training them and everything, is just getting the software installed, because TensorFlow is really at the back end C code, but then Python on top, and then we're using R to wrap all of that up. So there's a lot going on. Sometimes it can be challenging. We can run this tf config to see TensorFlow is loading right. So we're running 2.4, version 2.4 TensorFlow and Python 3.9. I think the newest TensorFlow is 2.5, but this is pretty close to it. So Keras comes preloaded with this handwritten digit data set. You can load it right in by calling this dataset MNIST function. And what it's going to come with are a training set and a testing set. So when you train your algorithm, you train your model, you're going to give it lots of examples that also have the answer you're looking to get from it. But in order to assess how well it does, after you train it, you also need to have a test set that's contains data that the algorithm has never seen. So you can take a look at this training data. We have 60,000 28 by 28 arrays. These are 2D arrays where the original image of the handwritten digit has been pre-processed already for us. I wanted to show how it looks if you look at the whole array, but I couldn't get it to not have these stupid dots in the middle. So if you were looking at this whole 28 by 28, though, you would vaguely be able to make out the handwritten digit that's in there. And so each of these bits represents a pixel in the image, and the value is 0 to 255, where, and this is representing grayscale, so 0 being the darkest, 255 being, I guess, absolutely white. And the labels are just integers, so this one up here was supposed to be somewhat like a handwritten digit 5. Oh well. And so we have all 60,000 labels here. And for the test set, we only have 10,000, but that's fairly large, and we'll be able to get a good idea of how this model is doing. So to build a model, you can use this function Keras model sequential. So the sequential model is pretty commonly used one. It's easy. You can just stack layers right in. For those without very much R background or no R background, we're using these pipe functions, which is going to take the output of what's on the left-hand side and use it as the first argument on the right-hand side of it. And this comes from R's tidyverse package. So we can build some layers. Dense layer means it's fully connected. So every node, every one of these 512 units in the first layer is going to be connected to every node in the second layer. We have to give an activation function, which is going to help with updating the weights in training, which is an iterative process. And we also have to tell the first layer, our input layer, what the input is actually going to look like when it's coming in. So here we have 28 by 28, because rather than giving it a 2D array, we're going to stretch that out into just a 1D array that's going to be 784 long, I guess. This final layer, the output layer, when you're doing classification, you can use this softmax activation function. And so we have 10 possible classes, 0 to 9. And what this is going to return is a probability for each of those 10 classes. And essentially, the class that it picks is going to be the one with the highest probability. So we can run that and build this model. The next step in Keras is we're going to compile the model. So a few important parts here. You need to supply an optimizer, which is what's actually going to be doing the learning. That's what's going to be, updating weights throughout. And the way that the optimizer is going to know how to update those is with your loss function. Again, it's going to essentially steer the model, say, you're learning and getting better, or you're not learning and you're getting worse. You can also give a metric, which I just have accuracy here. From my understanding, this isn't used in training. The loss function is really the overall measure of success, but the metric is good to track as well, just for our own sake in watching the training and iterating through different model configurations. And this loss function, categorical cross entropy, is some type of blend of false positive, false negative sensitivity. I don't know exactly how it works. And one other thing I wanted to note that may look kind of odd is when I look at this line here, my intuition would be to say network, assign network is network piped into compile. But the way Keras works, you can just essentially compile it in place. So we'll compile it. Like I said, rather than using the big 28 by 28 arrays, we're just going to stretch it out into one flat layer. And we can use this Keras array reshape function. And we're also going to scale all of the digits in each image. Again, they take the values 0 to 255, so divide them all by 255, and then they'll all be 0 to 1. And you can put them in their raw form to the model, but I think having smaller values increases the learning rate or makes learning go a little bit faster. We're also going to do a maneuver called one-hot encoding for our labels. So rather than just giving an integer as the label, 0 to 9, the final output, again, is going to be 10 probabilities and a probability for each class. So for your answer, your target or label, you want to have a 1 in the place of the correct class and zeros all the way across in every other one. And finally, we get to the fun part. So this Keras fit function is where we're actually going to train this model. So we're going to pass it our train images, which are already formatted, our labels, which we already did one-hot encoding on. We're going to tell it how many iterations to train for. Here we're doing 5 just for the purpose of showing, the basics of this network. And it also does work really well in a very short amount of iterations. But this decision for number of epochs and also the chunks of your entire data set that you're flowing through at once are both arbitrary decisions that you kind of have to experiment with. I don't think there's any right or wrong way to come up with these other than just training your model multiple times and adjusting those. Just one other note, this batch size. So rather than putting all 60,000 of those images through the network at once, we'll break them down into smaller chunks. And again, this is just something you have to play with. So we'll go ahead and let that run. Hopefully, if everyone during this tutorial is running this, the Jupyter Hub will be able to handle it, but I think we'll be fine. And kind of a spoiler here that I told you it does do really well, but now that we have this trained model, we can evaluate it and we can give our test images, remember, which we withheld in the beginning. The model has never seen these, and along with their labels. And it'll come back with a final loss function or loss score and an accuracy score. So 98%, not too bad. 9,800 of the 10,000 test images were correctly classified. And in general, just accuracy, obviously ideal would be 100%, but you want higher accuracy and lower loss. Loss closer to 0 is good. So that'll be it for this first tutorial. I'm going to jump back into some slides. Are there any questions, though? This might be a good time to take a pause.
Yeah, there's one question just come through. I have a question myself. I'll quickly ask it because it's related to this last point. You said you just play with the epochs and the batch size. Are you just ultimately looking at your output of loss and accuracy till they're as good as you want them to be?
Right. Yeah, you can just continuously adjust your model architecture, go back and compile it, and fit it over and over. As you saw, I mean, it's not too many lines of code, and it does run pretty quick. So yeah, and I, for some reason, always do stuff that's like base 8, but I don't think there's any reason for that. I mean, you can do whatever and just play with it. experiment.
You like base 8. Okay, great. Benji also has a question. He has multiple questions. So first, in terms of layers, are there any transformations or filtering of the original data?
So in this example, not so much, but if you get really technical into neural networks and you're building, for example, like image classifiers, like putting in actual images, which they are capable of, you'll have to do filtering layers and a lot of other stuff like that. Yeah. Yes.
Cool. Next part, do we even need to know the transformation that has been done to use the layer?
I guess you kind of learn it with experience. I mean, the transformation, I guess I've mainly used these dense layers, again, the fully connected, but yeah, there's lots of other layers that you can look up in the Keras documentation that do other types of transformations.
Third, is there generally a predictable trade-off between adding arbitrarily many layers of the same data versus repeating the training iterations?
So having too many layers can be a problem, and also having too few layers can be a problem. And part of the bummer about doing this tutorial in a notebook rather than in RStudio is normally when you call this fit function, you'll get a printout of each epoch. So each iteration of training, what the loss and accuracy are for how the model's performing on the training data. And you can tell, is it getting better or worse? And you'll also have a little plot. I think I have the plot in the next one, but maybe I just forgot to add it here. But you'll be able to tell. And one thing you're looking for is what's called overfitting, where you can have a model that's, you might have pretty simple data, but then you have a model that's really complex and learns too much about the training set that is so specifically tuned to just those examples that it can't generalize and perform well on data it hasn't seen. So
I'd actually like to chime in here. I think that at least in Python, when we're fitting models, you can add a argument of verbose. If you type verbose equals 1 or 2, then you'll get a printout for each iteration. And I believe that exists in R as well.
I tried, yeah, I know a lot of it's like, if you're, I've been mainly using Keras in R, and a lot of the documentation is for Python. So usually I try those, but didn't work here. Yes, so.
Turner has a question. Our accuracy was 0.96. What's the reason for different models trained on the same data to produce different accuracies?
So every time you build a model, even if you're using the exact same training set and testing set, it will vary, because when you first initialize the model, all of the weights kind of get randomized, I guess. And so it's kind of like you're just resetting it and throwing all that data in there and seeing how well it'll do. Usually though, you won't get accuracy variation that's really far. You won't see a drop like 20 or 30% if you're testing it like 10 times in a row on this. It might vary a few percent, but yeah.
Okay, great. I think we're good to move on to the next part.
So this is OceanHackWeek. I haven't really showed very much ocean related stuff yet. So the next tutorial is going to be related to my project that I've been working on with Nick. So in Maine, there's a harmful algal species that produces a toxin that's can cause serious health problems in humans. So Maine Department of Marine Resources, the management agency, will go through the Maine coast and test weekly for this toxin. And if toxin levels rise above a certain threshold, the fishery gets shut down. So this is for oysters, mussels, clams, even scallops too, I believe. And so this presents a challenge for people that are growing them or harvesting them, because having an unforeseen closure, especially during peak season, they usually take place during the summer, can cause serious economic loss. So we're working on developing a forecast that's site specific to predict shellfish toxin levels. And the toxin is PSP, paralytic shellfish poison, and it can actually kill you if you eat toxic shellfish. So this screenshot here is a little clipping from an interactive web page that we're rolling out. You can see this forecast is live. We're in the 15th week and it's been going all right. So what does this data actually look like though? It's a table that has, the toxin testing was started in 2014. So we have toxin testing goes on at about 100 or a little over 100 different stations. And we get a total toxicity reported. And this is a sum of individual toxins. There's actually 12 in the data set, but I kind of simplified just for the purpose of this little trace. We also have a gap days column because sampling takes place roughly weekly, but in order to group samples together and say they're sequential, essentially, we need to filter by minimum and maximum gap. And our forecast isn't forecasting the actual total toxicity level. We're using a classification system where 3, the highest, is a closure level. That would mean, or that would be a prediction for the fishery is going to close. So walking through this data, we can pull out some images, or what we refer to as images, which are 2-dimensional arrays. So you have the dimensions X, which are the number of variables or features. These are the toxins, and there's also some environmental data that I added in there. We've been testing out to see if it improves model performance. And your other dimension is the number of weeks in each image. So we can pull that image out. We store the 2D array along with our label is going to be the following week's classification, because we're forecasting 1 week ahead. And we also store some metadata, date, location. And so we slide through and pull out all these images. And again, I only show one site and a few rows here, but I think there's about 13,000 measurements in the complete data set. So then we have this list of lists where one element of each list is that image, that 2-dimensional array. But again, this isn't going to work for Keras input or neural network input. So we're going to do a series of maneuvers. So first, we're going to smash all of these lists into one big 3D array. So now you have 3 dimensions, again, the number of variables by the number of weeks in each image by the number of images we've pulled. And you can use this function abind in R to do this. And then finally, we're going to basically combine these 2 dimensions, X and Y. So now we have a 2D array where each row is one of those images stretched out into a 1D array. And again, this is using Keras array reshape. To make this step a little more clear, on the bottom, we have our raw data, and on the top, we have our neural network input. So for example, for this image we're pulling out, we have 1 week here, 1 week here, and 1 week here, along with our labels. And with that, I'll go back to the Jupyter Hub. So now we're going to fire up this number 2 shellfish toxin forecasting notebook. We'll start by, again, making sure we specify the environment. We're going to load Keras, use some dplyr as well. And also for our forecasting, we have all of the code wrapped up into an R package, but just for making it simple, I threw all of those homegrown functions just into an R script so we could source them here rather than dealing with all of the dependencies of that package. We can read in the raw data also. I've just put it in a CSV format here. In the actual experimental operational forecast, we serve it with a package, but it's in a CSV here. I shaved it down to just the years 2014 to 2017. Again, we have our station ID, the date the sample takes place, our gap. Classification all says 0 now because it'll get assigned in this next step. We have our total toxicity. We have 12 individual toxins, which sum up to this total. And then we also have a mirror sea surface temp, cumulative sea surface temperature, and 8-day rolling average of photosynthetically active radiation. One other maneuver I'm going to do is log all of the toxin variables because they're all log normally distributed. Most of the time, toxin levels are low, if not 0. And then we get these few really high tests each year. So to smooth out that distribution, we do a log 10 plus 1 on all of those with this other homegrown function. Next up, this algorithm or this function make image list is going to do that first step of walking through the entire table, going by site and by year and pulling images out. You can tell it the bins you want for your classes, the number of weeks in each image, the number of weeks ahead of the image, because we've also been testing, you know, a longer range 2 or 3 week forecast, minimum and maximum gap. This is just because, again, testing is roughly weekly, but often it's not even 7 days each week. And we can also tell it which toxin and environmental variables we want to include in each image. I'm going to run it because it might take a second. And then we'll split all of these images, have a year label, and in order to test on one entire season and train on all of the rest, we'll split it up by year. The only reason I did 2015 and then these 3 is because this one worked a little better for the example, but you can play with this notebook on your own after. And then we're going to use this other function, pool images and labels, which are going to make these train and test objects. So you can see it has the elements, the image, which is that big 2D array. Each row is one image, and we're using 13 variables, 12 toxins and 1 environmental by 2 weeks. So we have 26 variables per image. The labels are 1 hot encoded. We have 4 possible classes, some other metadata in here. And here's a little glimpse of the 1 hot encoded labels rather than just passing in a straight integer. So again, I'm using Keras's sequential model here. More layers, again, not for any reason. This isn't necessarily the best hyperparameter configuration, but I kind of did that on purpose to see it. You know, if you are interested, you can try playing with this and let me know if you get it working really well. And another thing I'm using here is called dropout. So I mentioned overfitting already. Dropout is a way to avoid it by dropping out some of the nodes that aren't holding useful information if they're basically not representing enough. And anything else we should point out? I guess we'll just build this model. You can use the summary function in R to get a printout of all of your layers. I put names on all the layers. I usually don't. It's just, I don't know, for this nice printout. You can compile using the same categorical cross entropy. And I have categorical accuracy here, but I've tested using either just accuracy or categorical, and it's the same. So I guess it was just from the code that I put in here. And finally, we're going to fit this model. So you can run this. So we're giving it the images with their labels, along with batch size. I'm doing 32 iterations, 32 epochs here. I tried verbose every option and couldn't get it to print out. So I don't know what the deal is with that. One other thing here, though, that's different from the last example is we're using a validation set. So you can do this one of two ways. You can specify a percentage to split off or manually make it yourself. But essentially the validation set is like another test set that gets run through the network during each iteration of training. So here I'm using 20%, and this is another way you can detect if your model is overfitting. If you start to see your training set accuracy going up and your validation set going down or staying the same, that could be a sign of overfitting. Yeah, if you do this in RStudio, these will all like plot live, and you can go really quick through tuning your model. And so we'll see how well this one does. You can also use predict classes and predict probabilities from Keras. So this will produce the same results as if you ran evaluate. So with your trained model, if you pass the same test set through the same trained model, those predictions will always be the same. But once you essentially refresh or build that model again, then you start getting a variable accuracy and loss. And so we're not doing too bad, 89% for 2015. We can put these results into a more human readable form. So I'm just making a table. I'm binding all of the probabilities on there, and we'll let it run for a second. This is the way we, when we generate our forecast each week, we send out a similar looking table. The only elements that are missing here are we add on 4 days for a forecast start date and then 10 days for a forecast end date, because these dates here are the last time each site was sampled. Not that interesting of a little sample of this table, but all zeros that were all right. But you can see in the probabilities that there is variability. Sometimes the model is really confident, 98% class 0 for this prediction. However, up here, you're kind of spread across. And so looking at these probabilities is sometimes a good way to tune your model and get a better idea of what's going on, because neural networks can be tough to interpret. And one final way you can get a more broader view of how your model is performing is by making a confusion matrix. So we have your correct predictions are along this diagonal, everything else is incorrect. You can see the model does really well on class 0. Again, that's an artifact of the class imbalance we have in our data set, because I think around 70 to 75% are low to 0 measurements. So the more data you have for each class, the better it's going to learn that class. And if you have less representation, it's not going to do as well. Just a few final notes before I take some questions. I really like this figure. I went to this Scale Transform conference a few months ago, and Andrew Nieg presented this. So if you're thinking, all right, maybe I want to make an AI product and put that into practice, here's some steps. Obviously, you're going to need to scope it out. Takes a little bit of background knowledge to say, is this a feasible project or not? Deep learning works well when you have a really specific task to tackle. You're going to gather data. The more data, the better. In general, the more data you have, the better the model will perform. And you're going to build your model and train it up. This can be a few iterations, testing. And finally, you pick one, you think it's ready to be deployed. And the key point here is that deployment is not an event, it's a process, because you're most likely building this product for someone else who's using it that wasn't involved. And so you need to go to them and say, is this working? You know, is it missing some things that it shouldn't be? And so you're going to have to iterate back to not only your model configuration and architecture, but also the data that you're using. You need to get more data, format it differently, or just use different data points. So with that, a lot of the content from this talk and the first tutorial came from this textbook. So if you're interested, it's great. Francois Cholet is one of the main contributors to Keras, and JJ Allaire is from our studio. And yeah, just on a final note, I'd say AI is booming. It's definitely here to stay, but keep your expectations realistic, because AI has gone through a few boom and bust cycles already. And this is the third, but I would say the most prominent for two reasons. We have so much data with the rise of the internet, and we have incredible advances in hardware, and we can run these models on GPU now. So I guess, thank you so much, and I'll call that the talk.
Thanks, Johnathan. That was great. It looks like we might not have any questions though. So